So first strategy, and this one is one because we see it a lot, is aggregation. So we'll combine two or more attributes or objects into a single attribute or object. So this can be where we are trying to reduce the scale of our data, trying to reduce the number of attributes or objects. So we could, for instance, combine two attributes, combine a high temperature attribute and a low temperature attribute in order to get a temperature difference attribute. We've now combined two columns into one column. All of the basically every algorithm has some time dependence on the number of attributes it runs, and certainly in terms of visualization and exploration, there's only sort of so many attributes that you can look at the same time or hold in your head at the same time. On the other hand, we might want to combine a bunch of different objects. If we have users who have many different sessions or who navigate to many different pages, we'll have dwell times that are different for every page and every session. And we might want to average all those dwell times in order to get one data object that is sort of the average user behavior for each user rather than the, 10 or 15 different sessions for that user. So the reason why we do this is exactly that. If we want to average user times, for instance, we're changing our scale. We want to aggregate cities into regions, states, or countries. We want to aggregate dwell times across sessions or across pages. And one of the big advantages of aggregation, particularly averaging, is that aggregated data tends to have less variability. It's a way of reducing the effect of noise. Well, it's a way of reducing the effect of random noise. If you've got human labeling errors, then you've got human labeling errors. If you've got, if you've got sampling procedure errors, you have sampling procedure errors. But if you've got random errors, say you're, random noise, then aggregated data will very much tend to reduce that. So as an example of that, and I really like this next page for this, these two are graphs of precipitation in Australia. So these are histograms. So the height of each block is the number of locations where precipitation was measured, which had, in this case, a standard deviation of between zero of the x value when we measured it on a monthly basis. So we're measuring the average monthly precipitation and measuring the standard deviation of that monthly precipitation at 500 different land locations in Australia. When we do that on a monthly basis, we get this very wide spread of standard deviations. Some places are very consistent in their rainfall. There's kind of these two peaks, and then you have this long tail of places that are just all over the place in terms of the variability in precipitation. On the other hand, if we take those exact same land locations and instead find the average yearly precipitation, the variance standard deviation of that, we get this very nice mostly single-peaked, very short-tailed histogram. We've significantly reduced our variability. We've reduced our random noise in our data set by increasing the scale, by aggregating our data over a longer time period. So that's one of the big reasons that we use aggregation.